Today, I'd like you to take a look at your force, mass, acceleration, post-lab check. Again, this is for part 2. If you've not completed both sides of this, I would encourage you to do that and then pause this video and come back once you've completed it. But for those of you who completed, let's take a look and see what kind of answers we got. So we've got a cart string hanger system, just like in the lab. This is called a modified Atwood's machine, and we're considering how the net force, mass, and acceleration are affected by one another. It says use the gravitational field strength constant of 9.8 newtons per kilogram in here. I may or may not have done that for each of the problems. Let's take a peek. In the experiment, what were our variables? Our independent variable was the net force. That's what we changed. The acceleration was what we measured at the end of each trial. That's the dependent variable. And our constant variable was the mass of our entire system. How did we keep the mass of the system constant? Well, we moved 4 20-gram masses from the cart. We put 4 20-gram masses on the cart before we started the trials. To increase the net force, we took masses off the cart and added them to the hanger. And therefore, the mass of the system didn't change. So that increased the net force by increasing the mass of the hanger, but because those masses were already within the system by being on the cart, the mass of the system was held constant. Keep cranking through. On number 4, it says sketch a graph for the experiment. We had an acceleration versus net force graph. What were the units? We would do rise over run, or change in acceleration divided by change in net force. So we'd have meters per second squared per Newton, because we found out that a Newton is a kilogram times meter per second squared. We could get rid of newtons on the bottom and replace it with kilograms times meter per second squared. So if we had kilograms times meters per second squared here, the meters per second squared would cancel out. We get 1 over kilograms for the mass. So what did the slope represent? The physical significance of the slope, or the term we're going to associate with that, is what did the slope represent from our experiment? Well, it was 1 over kilograms, which sounds like a mass, but the mass would have to be on the bottom. So we said it would be the inverse of the mass of the system. 1 over the mass of the system, or the inverse of the mass of the system. Checking out number 8, it says if the mass of the system was 0.5 kilograms and the mass of the hanger is 0.1 kilograms, and the acceleration is 1.96 meters per second squared, what is the net force acting on the system? Now, this is a problem I set up intentionally to have 2 ways to answer the question. In the lab, we figured out the net force by looking at the mass of the hanger and just finding the weight of the hanger. So that's one way to calculate it. Let's see which way I did it first here, and that's what we have here. To calculate the net force, it's simply the weight of the hanger, so it's gravitational field strength constant on the Earth times the mass of the hanger. We use 9.8 newtons per kilogram times the 0.1 kilogram, and that would be equal to 0.98 newtons. Now, there's another way to do this problem, and you would only be able to do this after you had completed the lab, where we had established Newton's second law. Acceleration is net force divided by the mass of the system. We now know that the net force, or we could solve this for net force, in which case net force is here, so we'd have to move mass to the other side. So we now have mass times acceleration. That's not a subtraction sign. Mass times acceleration is the net force. We've got a half a kilogram times the acceleration of 1.96 meters per second squared, and half of 1.96 is 0.98 newtons. So we get 0.98 newtons whether we use Newton's second law or we went back to the original idea that the net force is caused by gravity pulling on the hanger. So simply the weight of the hanger is the net force. Next up, you want to double check your units. These may or may not be in the same order they are on your paper. By the way, the other problems in here, the values might be similar, they might be different, but how to solve the problems would be the same. I'm noticing on here that there's a set of units that we didn't use. We got meters, meters per second squared, kilograms, newtons. Which one are we missing? Did you think? Gravitational field strength constant on the Earth? That's the one that's missing, but hopefully you can match all those up. Next. The next 3 problems didn't make it on your worksheet, but they're valuable ones to be able to solve. Definitely things that are quizzable based on the problems we've worked on so far. It says on the next 3 problems, the works are not on the worksheet, but you need to know how to do them. Perhaps add them to the empty space at the bottom of side 2. You're supposed to imagine the same kind of setup we had in class, but now we have a cart that has a mass of 1.1 2.8 kilograms, a hanger with a mass of 0.3 kilograms. So that's important information for us to remember. I'm going to go ahead and highlight these. So we've got the mass of the cart is 1.8 kilograms. The mass of the hanger is 0.3 kilograms. And we set it up like a modified Atwas machine, the cart, string, hanger, the pulley. Number 10 says calculate the net force. Well, how did we calculate the net force in the lab? Now remember, we didn't know Newton's second law yet. So we had to know what the mass of the hanger was, right? The weight of the hanger is actually the net force. Gravity pulling on the hanger is what caused it to speed up, so we need GCB times the mass of the hanger. We use 9.8 or 9.81 newtons per kilogram. I'll be pretty flexible with you depending on which of those you use in here. We go times 0.3 kilograms, so 0.9 times 0.3 is going to be around 3. So you got a net force of 2.943 newtons. So that's how hard the gravity is pulling on the hanger. That's the weight of the hanger, and it's causing the whole system to speed up. Next up, we're asked to calculate the mass of the system. Now, this equation we have up here we use pretty commonly. How did we find the mass of the whole system? Well, we may not have written it out this way, but if you remember looking at your data columns, we took the mass of the cart plus the mass of the hanger to find out the mass of the whole system. So the mass of the cart in this problem was 1.8 kilograms. The mass of the hanger was 0.3 kilograms. We are assuming that the string is massless for this, so you just add those together and you get a mass of a system of 2.1 kilograms. Lastly, we want to find an acceleration. Using Newton's second law, if we know the net force and the mass, we can find the acceleration. So we start by writing Newton's second law, acceleration net force divided by the mass of the system. We replace the net force with our 2.943 newtons. We divide it by the mass of our system, 2.1 kilograms, and 2.9 divided by 2.1 at 1.4 meters per second squared. Again, these weren't on your paper, but you could probably add them below there's empty space in the bottom of it too, because this somehow got chopped off when I photocopied. Let's take a look at what's on side 2. These are also listed as 10, 11, and 12 in your paper, but they were greater numbers on earlier ones. So looks like the values I have here are similar to the worksheet. We've got an acceleration versus net force graph. We've got 2 lines. The less steep line is marked as, oh, you know what? On your sheet, it's marked backwards with the numbers. So the numbers are going to be off, but the steepness of the slopes are going to be the same. So let's see here. Maybe I can change color and go. It looks like on your paper, this one is B. And it looks like on your paper, this one is A. So we've got state the relationship between acceleration and net force. How do you know? Well, because there's a y-intercept of 0 and you've got a positive constant slope, we can say acceleration and net force are directly proportional. Which cart would have the greatest acceleration for 1 newton of force? Well, if I just pick some random newton of force, so we do this, which one of these would have a greater acceleration? The one represented by the red line or the one represented by the blue line? And obviously, we get a greater acceleration with the same net force for object A, which has the steeper line. Next up, write an expression with the relationship with net force for each of these. Once again, I might have the letters mixed up on these because I had done these ahead of time. And that's what it looks like. It looks like A and B, and A is the steeper one. So it looks like, let's see if I can just grab these and pull these around. Not that way. Anyway, these are opposite of one another. Object B has a less steep slope, and we'd have y equals the slope times what's on the x-axis. So for object B, we'd have acceleration as 4 meters per second squared per newton. And for cart A, the steeper of the two, you'd have acceleration is equal to 8 meters per second squared per newton times the net force. Next up, it says, what was different about cart A's setup compared to cart B? In other words, why did A have twice as big of a slope, the line that represented cart A's setup have twice as big of a slope as cart B. So think about that. What would that mean? Why would cart A, who has a steeper slope, have a greater acceleration even though we pushed equally hard or pulled equally hard on it? What does it have to do with? It has to do with the slope, right? What does the slope represent? It represents the inverse of the mass of the system. So how would you figure that out? So again, these letters are probably backwards. So I'm going to just switch this to B and switch this to A. So A, if you took the inverse of the slope, in other words, if you took the slope upside down, 1/8 of that would be 1/8 of a kilogram would be the mass of cart A, or of A's system. And for B, you do 1/4, which would be 0.25 kilograms. So this to me looks like object A with the steeper slope had half as much mass as the less steep slope with the B setup, because we had a bigger acceleration on A than we did from B. All right, that is the end of that, and I think we now need to take a look at percent error. To do this, you're going to have to maybe pause the video and go find your actual graph, and you're going to have to find the slope of your graph and the mass of your system to figure this out. Please unpause when you have that information. Great, welcome back. So write down the slope of your graph. I'm going to pretend my slope is 3 meters per second squared per Newton, and I'm going to write down the mass of my system as 0.320 kilograms. Your numbers should be in that ballpark, but maybe not exactly the same. Next up, let's calculate the inverse of the mass of the system. So literally take the number 1 and divide it by whatever the mass of your system is. For mine, I got a value of 3.125 meters per second, 3.125 1/kilograms. Now, for any percent error, you're supposed to take the scientifically expected value of the slope minus the slope. Remember, we take the absolute value of that difference and divide by the scientifically expected value of the slope and then multiply by 100. To make it specific for this one, though, that means the scientifically expected value is 1 over the mass of the system. We need to subtract from that our slope, take the absolute value of that difference, divide by 1 over the mass of the system, and multiply by 100. So 1 over the mass of my system was 3.125 1/kilograms divided by my slope, which was 3 meters per second squared per Newton. And remember, this converts over to 1/kilograms as well. So we take the absolute value of that, and 3.125 minus 3 is just 0.125 divided by 3.125. 1/kilograms divided by 100. Notice that the units cancel out, 1/kilograms divided by 1/kilograms, and our final answer is 4% error. Remember, that falls under the 5% rule, so I wouldn't have to explain what errors I had made. So if you have any questions, please feel free to touch base with me, but you should be prepared to turn in all of these Part 2 chunks of our lab, the data sheet, the Part 2 lab, the post-lab check, your mathematical analysis, and your percent error at the beginning of class on Thursday. I hope that helps.